Most machine learning algorithms involve optimization of some sort, which refers to the task of minimizing or maximizing a function f of x by changing the values of the input x. The convention is to minimize the function, and if we need to maximize it in some scenario, we will minimize minus fx instead of maximizing fx. This keeps things less confusing and consistent. The function that we want to minimize is often called the objective function. It is also called by other names such as cost function, loss function, error function, etc. This is the function which we define using the problem that we want to solve using an appropriate choice of properties that make the function easier to deal with for the optimization task. The convention used for defining the value that minimizes or maximizes the function is denoted by x equals argmin f x. Our goal is to find this optimal value, or a similar value not so optimal in some cases, that minimizes our objective function. Gradient descent is one of the most fundamental optimization techniques used in machine learning. But what is a gradient? On what do we descent down, and what do we even optimize in the first place? Gradient descent sometimes defines an analogy of blindfolded man who is trying to find his way from somewhere mountainside to the lowest point of the valley. Actually, he cannot see the topography, so he takes a step in the direction with the steepest decline. He then takes another step again. The sizes of his steps are proportional to the steepness of the terrain at his current positions. He takes big step when the terrain is steep. The man takes smaller steps as terrain becomes less steep. If he were to continue taking large step, he may accidentally step over the valley's lowest point. He would then need to change direction and step to the lowest point of the valley again. By taking small step, he can avoid stepping and forth over the lowest valley point. The blindfolded man walks until he cannot take a step that will decrease his altitude. At this point he will find the bottom of the valley. Formally, gradient descent algorithm is an optimization algorithm that can be used to estimate the local minimum of a function. A plot of one variable convex function looks like this. The bottom of the curve is the sole local minimum. Non-convex function have many local minima. The plot of their functions has many local peaks and valleys. Gradient descent only guarantees to find the local minimum. It will find a valley but not necessarily to find the lowest valley. In summary, here are the links between the mountain analogy and the mathematical function to minimize. Analogy of the mountain. Function to minimize. Valley. Function. Slope of the valley. Derivative of the function. Distance traveled. Learning rate multiplied by the derivative. Initial position. Initial coordinates randomly chosen. Bottom of the valley. Minimum of the function. Assuming that this curve is of our function to be minimized, we choose a random initial value of x. We will move in the opposite direction of the gradient with a step equal to the derivative of f in x multiplied by the training rate alpha. This step brings us closer to the minimum. The next step consists in repeating the same process to get closer and closer to the minimum of the function. It should be noted here that the steps will get smaller and smaller with each iteration, since the derivative decreases as we get closer to the minimum. The learning rate is an important hypermeter of gradient descent which controls the size of every step. If the learning rate is small enough, the function will decrease with each iteration. If the learning rate decrease, however, the time required for gradient descent to converge increase. The algorithm will take longer time to reach the minimum if he will take small step, but if he will take large step it may repeatedly overstep the minimum. That is, gradient descent could oscillate around the optimal values of the parameters. The algorithm works as follows. Given a function f, we want to run gradient descent on. Get the starting random position x on f. While not convergence, repeat. Compute the derivative of f at point x. Multiply the derivative by a negative step size, minus alpha. Usually alpha is a positive value and smaller than 1. Compute the next position of x on the surface by adding the rescaled derivative to the value x. We will use Python on the Colab platform to run gradient descent on a function f of x to find its minimum. The first thing we will do is use those libraries. Then what we should do is to define the function we want to run on the gradient descent algorithm. Here we will try to find the minimum of the polynomial function 3x squared plus 2x plus 1. We set value of the learning rate alpha and stop conditions. We then run the gradient descent. While running this algorithm, we save in each iteration the position reached on the curve in x cache and y cache. In those two variables we will have the history of the coordinates of all the positions. Here we plot the curve of the function and the first positions of x computed by this algorithm. We can create an animation in which we illustrate the progress of the algorithm. For this we will need these libraries, then we plot the curve of the function. After that we create the objects that will be animated and then we initialize them. For the animation, we plot, at each iteration, a point at the position indicated by the algorithm and we display the number of the iteration. To create the animation we use the function animation funcanimation and then display it. For this second example, we apply the gradient descent algorithm on a function with several local minima. We will take as an example the cardinal sine function of 0.48x. We will execute the code twice by changing the initial value of x each case. We notice that the algorithm converges each time to the closest local minimum. In summary, the gradient descent algorithm is a very powerful optimization tool for approximating the local extremum of a function. The efficiency of the algorithm is conditioned by a good choice of the alpha learning rate and the initial value of x. Well, that was all for today. If you have any doubt, feel free to add your question in the comment section. Thank you.